Okay, we're going to continue our discussion about the step response. The step is a common test signal in our field. It's kind of akin to just stomping on the gas pedal or turning something on. And we want to see what the response is when we turn something on or apply step input. And so this is just the idea of a second order model. It's a little bit more sophisticated than a first order model. Some simple systems could be modeled as first order, but the next most easy problem is a problem that might be a second order. We'll talk a little bit about more complicated models that are higher order than second order on another day. But today, let me first say that if we take a look at this second order model, what we're going to do, the first thing we're going to do is we're going to focus on this denominator right here and take a look at the roots. And since the roots of the denominator, we also call them poles. Okay, and as I mentioned in a previous meeting, this is one thing that we want to kind of brush up on how to do. There's a lot of various ways to do it. You can use quadratic formula, which I will try to avoid requiring you to do, but you can certainly do that. Quick question?
Is that a 6S on the top in the numerator?
Is that a 6S? No, that's a B0. That's A1 and A0 and B0. So A1, A0, and B0 are just constant. Let's make that A0, A1, and B0 are just numbers.
Thank you, sir.
Maybe I shouldn't use B. Maybe I should use gamma. Let's use a Greek letter. Really throw people off. Don't dwell too long on that because I'm probably not going to use this A1, A0, B0 past this slide because it's not really a standard form. We'll talk about the standard form in a minute. I'm just saying that we're looking at a model where it's a constant up here. Give it your favorite name. Put a real number there if you want. And put a real number here, here, and here because we're not going to use it again after this slide. The idea is that it's a second order polynomial in the bottom. We want to examine the roots. That means we want to find the roots of a quadratic equation. You can use a quadratic formula. Or you could use your calculator and use your root solver. I don't know what the command is because I don't carry a calculator. I don't carry a cell phone, so I don't know how it's done. But I know it can be done quickly. All right. What I typically do, a lot of times I might give you an example where I try to set it up so that when you look at it, you can instantly say, oh, I know what the roots are of that thing. And you say, how can that happen? This is just a quick note. Okay, that's s plus 2 quantity squared plus 3 squared. I want to find the roots of that. In other words, the number s that makes that equal to 0. You could multiply it out, and you can say, well, this is the same thing as s squared plus 4s plus 4 plus 9, or that's s squared plus 4s plus 13, and then use quadratic formula. Okay, go down that path. It's all mathematically correct. But my intent for doing that is not, writing it this way, is not to make busy work for you, force you to go down this path so that you can get to a form that uses the quadratic formula, or that you can use a form that you can plug into your calculator. What I'd like for you to maybe remember for this class is if you see something like this, just remember that Dr. Hung is your friend. He's trying to help you out. And one of the tricks of the algebra trade is to recognize that you see something like that, the roots are going to be s, 1 and 2. They're going to be complex constants. They're going to be negative 2 plus or minus j3. Okay? So this 2 comes from here. And this 3 comes from here. So yeah, you could go down this path. it's okay, but not necessary. It's okay, but not necessary if we remember some patterns. Okay, and the pattern is if you see something like this, if you see it on a test, and you'll see it on some of my tests, you say, why did Dr. Hung write a quadratic formula that way? It's to save you some calculator time. Okay. But if you go down this path, it's okay. It just means that I know you didn't come to class today and didn't get that tidbit. All right? All right, so when it's a quadratic formula, a quadratic equation, you also know that sometimes the roots are not going to be complex like this. They may be purely real. That can happen as well. But the case that we're interested in studying is the case of complex roots. So let me just say that roots may be three cases. They could be real and unequal. They could be real and equal, or they could be complex conjugates. They could be a complex conjugate pair, like -2 plus and minus j3. Plus and minus. Okay, that's what that is. Plus and a minus. Okay. This is the case that we're going to take and focus our attention on. Okay. The reason we focus our attention on this particular case is because it gives the most interesting time response. All right. And let me sketch the time response for all three cases. Let me sketch the step response. The typical step response for the first case is going to be something that starts, this is in time now, it's going to gradually start off and then respond and then eventually get to where it will settle out, assuming that the response is stable. Okay, if it's unstable, it'll blow up. But if it's stable, it will eventually get a balanced response. The real and equal case is faster. It's going to give you a faster response. And it is the fastest response that you can get without doing something like this. Okay, so this is case 1, case 2, and case 3. This is case 1, this is case 2, and this is case 3. Case 1 is called the overdamped case. Case 2, where the real and equal roots, is called the critically damped case. It's the fastest response that we can get out of a second order system before it overshoots. This is called overshooting the mark, and then undershooting, then overshooting, then undershooting. Okay? These two cases, case 1 and case 2, it's a little bit difficult to fit models to them because there are not many features to see here, other than to say, well, it starts here and it gets there, and I can kind of guess maybe the settling time, but it's really difficult to distinguish between whether it's overdamped or critically damped at times. You just know that it gets from here to here. But the underdamped case has a lot of features. Not only can we tell how long it takes to settle out, but we see that we have these things that really stand out. The fact that it overshoots and undershoots, we can see kind of frequency behavior. It's rich with information. And because of that, there are formulas that can describe this response, and then we can fit a model to it. Okay. So this is called the underdamped case. And this is the case that we're going to study. We're going to study the case where we have a second order model and the roots are complex conjugate pairs. Okay. So here are some of the features. Again, I'm going to sketch the response. This is the time. And so the features that we will be interested in looking at are, if we apply an input, this is the response. It'll probably respond like this. It starts off gradually and then it moves quickly to where it's supposed to be, but it doesn't stop there. It overshoots, then undershoots, so on and so forth like this. Okay. So we're going to be interested in knowing what is the final value going to be. Okay. We're going to be interested in seeing how long it takes for things to settle down again. I'll call that item 2. We're going to be interested in determining how much time it takes to get to the first overshoot. This would be number 3. The time to the first peak. Okay? Time to the first peak. And we will also be interested in kind of getting an idea of how big this is. Okay, well, I'll call that the overshoot. How big is that? Okay, so these are some of the characteristics that we can determine. We can sometimes also, if we have enough wiggliness, we can kind of estimate what this frequency is. But that's additional information. The point is, there's a lot of interesting features that we can see in an underdamped response. Okay, underdamped response. Okay, so let me give you the standard form of the model that from which we can extract some model parameters, and then maybe we'll step through some examples. All right, so standard form. I'm going to give the standard form and then maybe rewrite it in some other forms that I think are more useful or easier to work with. Okay, so the standard form in textbooks, we're going to have a gain, and then we're going to have the second order term over here. You thought my handwriting is bad, now it's really going to get bad because it's going to involve Greek letters. Okay. So there are a total of 3 parameters in the model. Okay, S is the variable; it's the frequency domain variable S. Okay, it's not time; it's S. But then we have 3 variables. K is again the DC gain. It's the gain of the system. If I put in a constant and wait for everything to settle out, the output should also be a constant, and the ratio of those constants is the gain. And remember, DC gain. You can also determine if you see a second order model, just remember we let S equal to 0, not delta equal to 0. Let S equal to 0. Let's see what happens if I let S equal to 0 here. And then I'll answer your question. If I let S go to 0, that goes away. If I let S go to 0, that goes away. And then I get omega n squared over omega n squared. That's just 1. And so this part has a gain of 1, and what's left is the gain k. Okay, I saw a couple hands raised, so let me answer that question first.
What is that letter between the 2 and the omega?
Oh, I'll get to it. I'll get to that letter. Let me get to K first. Second question. Saw another hand a minute ago. Maybe I didn't. Just scratching an inch. All right. What's the letter? Zeta, little zeta.
A Y that's on a lot of drugs.
Yeah, a Y on drugs. Okay, zeta. Okay. Whip out your calculator right now and Google zeta. Maybe you'll get a better picture. All right, zeta. What was the joke? Do we really have Google on your calculators? Oh, I've been seeing amazing things on calculators. All right. This is called the damping factor. The damping factor or damping ratio. It's really a damping factor. Okay.
Are you sure that's a zeta?
Do I think that's a zeta? I think it is.
I mean, I'm looking at it and you have squigglies that you shouldn't have.
Like I said, my handwriting's not good. Hey, look, I'm Chinese. You can't expect me to write Greek letters. It's a zeta. So if you can write a better zeta, I commend you. Okay, that's this omega. Omega underscore n. Okay, this is the undamped natural frequency. Okay. Now, from this standard form, it turns out if you plug this into the quadratic formula and work with the coefficients, you're going to end up, the roots are negative zeta omega n plus or minus j omega n times the square root of 1 minus zeta squared. Okay, I'll leave that out for a moment. Minus zeta omega n plus or minus j, and the imaginary part is omega n times the square root of 1 minus zeta squared. Okay, enough of equations. Let me sketch what this means geometrically. Okay, so let's plot the roots in the S-plane. This is the real axis, this is the imaginary axis. If we have roots over here, that's bad. It means the system is unstable, so we're not going to plot the response. So therefore, the roots must lie over here. Furthermore, the complex conjugates of each other, it's a complex conjugate pair, which means it looks something like this. Okay? Now, I can draw a line to one of the x's. I could draw a line to this x if I wanted it to be the same length. Okay? The length of that line is omega n. This line makes an angle here. Let's call it theta. Okay? Squiggly, zeta is the cosine of theta. So you can think of zeta and omega n as kind of being related to a polar representation of where the x marks are. I need to know what the angle is. I can get the angle if I know zeta. Okay. And I need to know how far out I need to go. That's a polar description. At what direction is the x mark? And how far out away from the origin is it? That's described by omega n. Okay. Zeta is a number that ranges from 0 to 1. Okay. As zeta gets smaller, the x marks move up to here. When zeta is equal to 0, that means 0 damping. Okay, that means 0 damping. When zeta gets larger, the x marks move down and move on to here. And when they are both right here, then zeta is equal to 1. That's critically damped. Okay. So think of it as zeta varies, then basically we vary the position of the x marks kind of on a circle. Okay, so here are two x marks. So that's the interpretation of zeta and omega n. One is called the damping ratio, and one is called the undamped natural frequency. Okay. It's called the undamped natural frequency because if the damping is 0, then the x marks are both right here on the imaginary axis, and we get a purely sinusoidal response. Undamped, meaning the damping is 0, that's the natural frequency. So if you have an ideal spring with no losses, the closest thing I can think of is I had a slinky when I was a kid. That's a pretty nice spring. The damping is really low, and it'll vibrate for a long, long time. Undamped natural frequency. Vibrating strings, that's the natural frequency. That's why it's called the undamped natural frequency. As the damping increases, the frequency will slightly decrease a little bit. And eventually you get to this point, and there's no frequency left at all, but you still get a response. And that's a critically damped case. Okay. Now, let's take a look at another way we can represent where these x marks are. We don't have to use polar coordinates. We can use rectangular coordinates. I can say, how big is this distance from here to here? Let me try to do that with maybe a red marker here. I can say that I could be interested in this distance. This real distance here. Okay, don't confuse this RE that's pink with this RE which is black. This is just labeling the real axis. I'll do that. Let me change that. Let me call this is the real axis, and this is the imaginary axis. This is the value along the line here. Okay. I could also say how big is it this way. I'll call this distance imaginary. Okay. So earlier what I said, the roots are equal to minus zeta omega n plus or minus j omega n times the square root of 1 minus zeta squared. This is the same thing as minus the real part plus or minus j, the imaginary part. So this is like using polar variables. Omega n tells me how far away I am from the origin. Zeta is the cosine of the angle. So think about this. What is the length of this? It's hypotenuse times the cosine of this angle. That's why it's zeta omega n. What is this? Distance, the imaginary part. It is the hypotenuse times the sine of the angle. And you think about it for a minute. If zeta is the cosine, then square root of 1 minus zeta squared is the sine. So you can rederive those formulas if you don't remember it. The books will typically give the standard form using zeta and omega n, because engineers like to talk about damping factors and undamped natural ratios, undamped natural frequencies, and damping ratios. But for doing quick work, I prefer to use the real and imaginary parts. It also saves me the headache of writing Greek letters. All right, so let's now take a look at, go back. We're trying to get this response, or we see this response, and we would like to characterize it in the model. All right, so let's write some equations for the different formulas, okay? Or the different characteristics. Let's write some equations for the different characteristics. Characteristic number 1, okay, is the final value. Final value of the response. The final value of the response is going to be equal to k times the input magnitude. Okay. K times the input, or maybe I should say the input amplitude. If the input is negative, the output could become negative. So the final values could be negative depending on if one of these numbers is negative. Okay, so this is just like what we saw on Monday when we were looking at the first order case. K is the DC gain. Gain has to multiply something. What does it multiply? It multiplies the input. So if you know how big the input is, then you know how big the output will be just by multiplying by K. Okay. The second feature is this thing, the settling time. Okay. Now on Monday, we looked at the first order case. I used the symbol settling time as TS. S is the settling time. And I said it's equal to 4 times the time constant. I can still use that idea of a time constant. What I want to think about is now that this response maybe had kind of an exponential envelope. And that exponential envelope is described by e to the minus t over tau. Okay, it's characterized by this tau, this time constant. And so it's 4 time constants. Now, how is that related to the Greek letters? Tau is equal to 1 over zeta omega n. 1 over zeta omega n. If we look back at a previous slide, we saw the roots are at minus zeta omega n plus or minus j, all this, the real part and the imaginary part. So the thing that the takeaway from this is equal to tau is equal to 1 over the real part of the root. So that's the settling time. Settling time is how long does it take for this thing to finally get within 2%. We're assuming that we're within 2% of the final value. If we want to get within 1%, we should change this number to 5, as I talked about on Monday. If we're satisfied to get within 5%, we can change this number to a 3. But most textbooks will use the number 4 for settling time. Okay, third characteristic. Third characteristic is this time to reach the first peak. And then it goes to second undershoot, and then a second peak, and then so forth. So, number 3, time to the first peak. P-E-A-K. T sub P. Okay. Well, if we look at this thing, what you see is this looks oscillatory. Okay, it's oscillatory. What is the frequency of oscillation? The frequency of oscillation is the imaginary part. Okay, the decay envelope is related to the real part of our roots. The imaginary part is the oscillation frequency. So this oscillation has a frequency, and that's equal to, it's close to omega n, but it's affected by the damping ratio. Okay? So when the damping is small, when zeta is small, zeta squared is even smaller, which means 1 minus a very small number is close to 1, and the square root of 1 gets even closer to 1, which means the oscillation is approximately omega n. But the units of omega are in radians per unit time, like radians per second. If I look at this time, I'm more interested in like time period. So I got to convert omega to frequency and get the period. There's a 2 pi in there involved. And if we derive everything, then the time to the first peak ends up being omega n square root of 1 minus zeta squared. That's the frequency. Turn that over, and then multiply by pi. Okay. There's a 2 pi in there, but the time to the first peak is half a period, so that's why it's pi. Okay, so this is pi. That's the time to the first peak. Or you could think of that as equal to pi divided by the imaginary part of the roots. Okay, so maybe you can see why I prefer to use rectangular coordinates and get the real and imaginary parts. I don't have to contend with that horrible equation. But I'm told that as electrical engineers, we are very comfortable dealing with either rectangular coordinates or polar coordinates. Right? We certainly are comfortable with it after we've been in a lecture with that amazing guy, Dr. Wentworth, right? EMAG, because you do rectangular coordinates, polar coordinates, cylindrical coordinates. All right. So the textbooks use zeta and omega n. The equations will be in zeta and omega n. I'm throwing them out to you using real and imaginary parts. Okay, the last characteristic we want to take a look at is this overshoot. How big is this overshoot? Okay, so number 4, and we need an equation for overshoot. And it is expressed as a percentage of final value. Okay, it's a percentage of final value. What I'm saying is, we usually take the ratio of how big this is, we measure it using this scale, we measure it, but then we normalize it by dividing by this. And so we always get a ratio that's less than 1. And then we multiply by 100 and call that a percent. And so there's a formula for the percent. So the overshoot formula goes something like this. The overshoot in percent is 100 times e to the minus zeta over square root of 1 minus zeta squared times pi. Try to zoom in a little bit on that. The overshoot is a function just of the damping factor, the damping ratio, the damping factor. Okay, let's see what happens when zeta is equal to 0. When zeta is equal to 0, what does this number become? Okay, zeta is on top and bottom.
0.
0. Times pi is,
0.
so e to the minus 0 is 1. So the overshoot is 100%. Okay. So if there's no damping, at all, the overshoot, this will be just as big as this. It'll be a sine wave that just oscillates around some value, up and down, up and down. Okay, it's 100%. Now let's consider what happens if zeta is 1. If zeta is 1, I got 1 here. I get square root of 1 minus 1 squared, which is, so I get 1 over 0, which is,
Infinity.
so e to the minus infinity is 0. There's no overshoot. Okay? So this is the formula that the books typically give. I recognize that I could put an omega n right here on top and an omega n on the bottom, and then I suddenly realize this is the same thing as 100 e to the minus the real part divided by the imaginary part times pi. Okay, so that's the formula I tend to maybe work with. Okay, let's do an example. I will need somebody with a calculator out there. Okay, so brush off your calculators. That's our model. 130 divided by s plus 2 quantity squared plus 3 squared. Okay, I could have wrote this as s squared plus 4s plus 13. Okay, these two are equivalent forms. Again, why did I write it this way? Because I'm your friend. No, I'm not your friend. Let's keep this separation between a teacher and a student. Let's not get too close. But I am trying to not cause you too much grief. You should be able to see that and immediately recognize the poles are at S1 and S2, the complex conjugates -2 plus or minus J3, from which we get that the real part is equal to 2 and the imaginary part is equal to 3. Okay. So from this, I then get that the time constant is equal to 1 over the real part, which is a half. And from the combination of the two, the real and imaginary part, I can use that information, and I get the overshoot. Let's calculate the overshoot, percent overshoot, is e to the minus 2 over 3 times pi, times 100. So somebody give that for me, please. I need e to the, roughly e to the minus 2, because pi and 3 are the same.
Yeah, -2 is 0.135.
0.135? 0.135? Is that exact or is that approximated?
That's exact.
That's exactly. Actually,
oh no, you said to the -2.
yeah. So if you roughly just say that pi is equal to 3, and say it's equal to minus 3, you get 0.135. If you actually use pi in your calculator, what do you get?
0.123.
0.123, 0.123, 0.135. Tell me what you did, okay? And so this is approximately 12 to 13%. 12 to 13%, okay? You have to realize when I started college, I didn't have a calculator. I used a slide rule. So pi was 3. Okay. Pi was 3. Okay. So let's see, what else can we get? We get time constant is, we know that, so we can get an idea how quickly it takes to decay. We know how big the overshoot is. Another thing we can get out of it here is let's get the gain. Okay. Let's get the gain out of this picture. K. What do? I let S go equal to 0 because it's the DC gain. Okay. To find K, just let S go equal to 0. It's the DC gain. DC means no frequency. It means S is equal to 0. If S goes to 0, then that goes away. This goes away. Or if I got this form to say that goes away, then I get 4 squared plus 3 squared is 13. Right? 130 divided by 13 is 10. Okay, so now I know how big the output will be. I can get an estimate for how long it takes to decay, and I can kind of sketch what that is. There's one more formula I can get. I can calculate the time to the first peak. Time to the first peak is going to be pi over the what? You could do 1 of 2 forms. You could look back in your notes, it's pi divided by this, or it's pi divided by the imaginary part. Okay? Pi divided by imaginary part is approximately 1, right? Because pi is 3. Approximately 1, okay? So let's sketch this then. Based on that information, we should create a sketch. Okay, has everybody got that written down? Any questions about how I came up with these numbers? All right, then let's sketch the response. This is time. Will the response be bounded? Will the response be bounded? Is there enough information on this page for me to determine whether or not the system is stable? Should be. Why? The roots are where? Right half plane, left half plane. Left half plane because of this. Okay, so it's stable. So it ought to be stable. So I'm not too far off by drawing this like this. I'm expecting the response to be bounded. I'm expecting the response to be positive because the gain is positive. And so the final value here is going to be 10 times the input. Okay? If I go to the lab and I turn on MATLAB and I use the step command, I enter this model into MATLAB and I use the step command. What is the assumption that the step magnitude is? What is the input magnitude? 1. It's assuming that the magnitude is 1. Okay, so then this will be 1. So the final value is going to be 10 times 1 or 10. It's going to do some wiggling. Okay, like this. And then it's going to settle out. TS is equal to 4 times the time constant. And we looked at our notes and said, where was the time constant? I get that from the real part. I invert the real part, it gets a half. So 4 times a half is equal to 2. Okay, so that's what this is. This is 2. Time to the first peak is approximately 1. So this is 1. And then what is the peak value here? Do I have enough information to determine what is the peak value?
It's like, what, 11.2?
11.2, 11.3. Okay? So the peak value here is 11.2, say to 11.3, depending on my round off. Okay, not 1.2 or 1.3, that'd be 20 or 30%. It's 12 to 13%. So this is 12 to 13% of 10. So you add it on to 10 and you get 11.2, 11.3-ish. Okay?
Would that be times the input? Whatever the input is?
The question is, does that have to be times the input? It's 12 to 13% of the final value. The final value is a function of the input. So if I double the input and get 2, then this becomes 20. And then it becomes 12 to 13% of 20. So yes, the input does have to be factored in. All right, so the topic today was the step response of the second order model. A particular type of second order model, the underdamped case. The overdamped case, it's a little bit difficult to see features that are interesting. Okay, so we generally don't have that in textbooks. Now there's ways to do it, and I'll talk a little bit about that maybe on Friday. Okay, how many days have we met?
5.
Okay, if I double 5, I get
10.
what happens on day 10 in this class? Exam 1. Okay, so you can pretty much say every 10 days is going to be a test. So we're halfway to the first exam. Now, one thing that you should probably note is I usually the first exam is going to be on a Wednesday. We got a Labor Day holiday in there. So I usually take the material for the exam up to 1 week before. So we still got another Friday, and then next Wednesday, and then next Friday, and then following Monday after that, and then we get the day 10. But the material is going to, for the exam, is pretty much going to stop next Wednesday. I'm going to continue presenting material on Friday and the following Monday, but I feel like most students haven't had enough time to absorb that new material for the next exam. So you can pretty much say there's an exam every 10 days, day 10, day 20, day 30. But the coverage for the exam 1 is going to probably be up to meeting number 7 or 8, something like that. Okay, so you need to take a look at that calendar. The coverage for exam 2, it's on day 20, but the coverage will probably go up to about day 17-ish, day 18, whatever 1 week before the exam day is. I'll try to mention that again on Friday. Okay, see you all Friday. I have a hard time remembering.